Hello, SWIC Earth Science students, and welcome to another recorded lecture. So this is week 10, Crustal Deformation and Mountain Building, which is chapter 7 of your textbook. I do want to point out this is a different note than is normally at the beginning of my lectures. I used to teach at my last institution a class called Structural Geology. It is an upper level class. It is basically just this, looking at deformation of the Earth. And I am aware I have a tendency to go a little bit more in depth on this and a little bit higher level. So bear with me. I will try to dial it back, and I will also try to always point out where I'm going more in detail than your textbook may. So just be aware of that. And I am also going to go back over how to study and take a test. I already did this. It's in one of the earlier lectures. The first time I put together this material, I had the thought, oh, maybe I should talk about this after the second test. The second time I taught it, I realized, nope, we should have that earlier. But I am going to still go over it again, just to remind you. So maybe after having two tests, you will look at this. So some basic concepts. Deformation. Deformation is something that is seen in rocks. It's also something that happens to rocks. So to define it, it is the measurable changes that have occurred in a particular volume of rock. So this can be changes in shape, it can be changes in orientation, it could be changes in volume. We define deformation by displacement. So basically we are going to look at individual points before and after deformation and see how those points' locations have changed. So displacement. A displacement vector is a line that has a defined length, which is magnitude, and direction, which is orientation, and that defines how a point has moved from its original position to its new position after deformation. A displacement field is defined by a family of these vectors, these lines, and this is what's going to define our deformation. The deformation path is the path that's actually taken by the rock. So displacement will always be a straight line. Deformation is typically not going to be a straight line. So it will often differ from that displacement vector. Okay. So I'm going to say a little aside here. Most textbooks have a tendency to introduce strain before they talk about stress. So stress is the force per unit area. This note here, your book introduces traction first. That is from my old class. So traction is stress in one direction. Stress is basically applying force per unit area, so you can think about it as pressure. Strain is going to be the changes in the location of points in a body relative to one another in response to stress. So strain is the rock changing due to stress, due to that pressure. So strain can be thought of as being translation, distortion, rotation, and dilatation, and I will explain each of those in a moment. We have different types of stress. So we can have what's called confining pressure, which is basically we are pushing or pulling the same amount in all three directions. Okay, that's what we see at this top. We're basically either squeezing it or blowing it up. Compressional stress is shortening, so we're pushing more on one direction and then we're going to be elongating in another direction. So if you can see here that these two arrows are pushing in, but this other direction is going to be pulling out. Let me get my pen. So if we're pushing in this direction, that means we're going to be pulling out in that direction. Tension is where we are pulling apart. Now, if we're pulling apart in one direction, the same thing that happened with compression, we're going to be pushing in the other direction. And then we have shear stress. So shear stress is the type of stress that we see at transform boundaries, and that's where we are sliding. It's like the scissor motion. So the responses to our stresses, so these are the stresses. The responses to the stresses are on the next page, so these are strains, displacements and strains. So displacement is simply moving points within without changing their relative position to each other. So translation is just sliding. So translation is we are just going to move things without changing the shape. We are simply sliding our points all in the same direction. Rotation will be this spinning. So we are going to spin our points. Again, they are not moving relative to each other. They are just spinning about some sort of a central axis. Those are both displacements. Strain is where we're actually changing the distance between points within the body. So dilatation, which can be spelled in two different ways. I pronounce it as the dilatation, but it can be spelled in two different ways, which is why they're both here. That is changing the volume. So we're either going to have things expand or contract, and that's what we're seeing down here, that in this case it's expanding. And distortion is where we're changing the shape. So that's what we see here in this one, that we have distortion happening, that we're changing our shapes. Okay, real world practice. So, real world practice. Describe the deformation you see. This is my parents' house. The first year I was in graduate school, a car decided to have a hit and run on my parents' garage. So it came up the hill, smacked into the corner of the garage, and then came on down, driving down the driveway. I still to this day find it hilarious that the car managed to miss every single object in my parents' yard, which there are many, and hit the largest object, which was the house, and only hit the largest object. So let's look at these pictures and see if we see different types of strain, responses to stress. So, translation, that's just sliding things. Well, do you see this here? That is dirt that was left from a flower pot. There was a flower pot sitting here that the car took with it. That would be an example of translation. It pulled that flower pot along with it. Rotation. Rotation's pretty easy. If we look at these bricks here, these bricks haven't changed shape per se. Like if we look at this set of bricks, it's just spun a little bit. Another example of rotation would be here, looking at the gutter and the siding, it's just rotated on an axis, it's just tilted. We can see that here as well, that this light and this piece of siding has just shifted, it's rotated. Let's see here. Dilatation. So dilatation would be changing volume. We didn't really see anything truly changing volume unless you want to think about the bricks that got like shattered. Potentially could be considered a change in volume. So there are some shattered bricks down here. And distortion, so that's changing the shape. Well, we can think about this brick facade, if we think about it as an entire thing, it's changed shape instead of, individual blocks of it rotated, but overall it changed shape. The gutter is bent up a little bit here at the corner. We can see that this area here is actually changing shape. It's not just being distorted, or I'm sorry, it's not just being rotated, it's actually being distorted. There was a better example of it, but I'm not sure where that went. I'm trying to remember what my better example was. So we do see most of the types of deformation in this example. And so basically what we're going to do with deformation is try to break it down to smaller bits that are easier to understand than to look at the entire thing. So let's look at these a little bit more. Translation, which is a type of displacement. So it's rigid body movement, and so it happens on all scales. So this can happen on a large scale, and the reason it can happen on a large scale is because when we go down to that crystalline lattice that makes up our mineral structure, we're actually seeing dislocation along those lattice. So we're seeing slip on the microscopic scale. That's what we're seeing here. So this is basically just objects sliding without changing shape. So here is a sidewalk. We can see it would have originally been nice and straight like it is here, and now we can see that these blocks have all moved slightly relative to one another. Translation is going to be typically a straight line, So it's basically the displacement vector. Here's an example where we can see the actual deformation path that this rock here took. So displacement vector is going to be the distance it went, which is the magnitude, so that's how far it went, and then the direction. So the displacement vector here is this line. So we have the distance, which is the magnitude, and then the direction. It's going to be a straight line. The deformation path is the path it actually took. So if we note on this picture, we can see this groove that's been carved that I just drove through in the pavement, and then we can see that this rock rolled a bit, so it kind of went crazy down here at the end. So it's not exact, the deformation path is not exactly the same as the displacement vector. The displacement vector is starting point to end point, straight line. Deformation path can go anywhere. When we're talking about deformation, a lot of times we're talking about scale. So scale is going to be dependent on, the deformation sometimes is dependent on the scale. So if we're looking at the very small scale, we oftentimes will see things as being rigid displacement. We see an offset. As we move to larger and larger scales though, moving further and further out, many times that what we know is rigid displacement will actually appear to be a coherent flow. So it'll seem to be non-rigid. An example of this would be if you took a deck of cards or a notebook or a textbook and draw on it, and you start to flip those individual pieces that you know are individual pieces of card or pages. They appear to make one continuous line when they're aligned with one another, but you know that if you're sliding them, that they're slipping along those individual planes because you know that there are multiple pages in that book. Same idea with with the Earth. So here we see what is obviously rigid offset. So this used to be aligned to that. There is a very obvious sense of offset here. Note that we're looking at 1 kilometer scale. If we go a little bit further out, that obvious sense of offset is not quite as obvious, and if we go even further out, it's going to be even less obvious. So this box here is the box over here. So now we can see that this offset, we do still see that individual offset, but it's getting less obvious. And if we went even further out, it would become less and less obvious. So this is what I was talking about, your cards. So here we have a stack of cards that have lines drawn on them. We know that this stack of cards is several hundred individual pieces of cardboard, very thin cardboard. If we squish them up though, we can see that those lines are no longer straight and they appear to be flow lines. But we know that those are individual slip planes. We know that each card is moving independent of each other. So again, deformation sometimes depends on scale. Rotation, rigid body displacement. So we're just spinning things about an axis. This is very common in geology. So these rocks, remember the law of original horizontality. Here are our bedding planes. These are bedding planes. Sedimentary beds do not deposit vertically, which means that these used to be horizontal and they have been rotated. So that's what the law of original horizontality tells us. Again, rotation is very, very common in geologic structures. To describe rotation can be complicated. We have to think about what are we rotating about. That's called the axis of rotation. So there's a point, a line that we are rotating around. We have to think about what direction we're rotating. So that's going to be clockwise or counterclockwise. That will depend on our viewpoint. So if you are looking at, depending on which direction you're looking at, you will see different senses of rotation. So if you're looking down at the North Pole, if you're looking down at the South Pole, we see different senses of rotation. The magnitude of rotation will be degrees, so how much have we moved degrees-wise. We kind of looked at this with some of our labs when we were looking at like time on the globe. And again, remember that rotation will depend on the direction of view. Most times in geology, we're not looking at, or not most times, but many times in geology, we're not looking at just one stage of rotation. Many times we're looking at multiple stages of rotation that have occurred over long periods of time. So we have to, they can be kind of challenging to tease it back out to its original state. So here's some examples of various rocks that have been rotated. So law of superposition and original horizontality tells us that rocks are deposited quasi-parallel, almost parallel to the bed surface, so they will follow the ground surface, and the oldest rocks will be on bottom. Whenever we see inclined strata, so things that are tilted, that tells us something has happened. So these sandstones, something has made them go like that. These sandstones, again, something has made them go like that. This is some sort of an igneous rock. Something, again, has made it go like that. When we are looking at rotated layers, sometimes we actually have things that are called overturned layers. And to determine if something has been overturned, we have to use some of the indicators within those layers themselves to see, are we still looking at the original top and bottom? We call that the facing. So is this the original top of the layer, or is this thing that's on top actually the original bottom? So what can happen is we can actually have layers that do this. And so if we look at this section, if we're going straight down, we're going to hit the bottom of the layer first. So that's what we call an overturned layer, where if we're going vertically down, we encounter the bottom of the layer before the top of the layer. We can also have rotation on the smaller scale. So these are, on a big scale, examples would be things like listric faulting. This is a type of normal fault where we actually have a spin at the bottom. So it will kind of be like scoop shaped, shovel shaped. And so we get rotation of that, we end up getting, each of these individual beds at the top will be rotated compared to each other. We can have what are called kink folds. That's what this is. So these are very tight little folds in the rock that cause basically a not a 90 degree, but a very severe rotation on a very small scale. So we can see that if we look at this, it makes this little Z shape. And we can also have rotation on, mineral scale. So here we have an example that this, this garnet was undergoing shear. So it was undergoing right lateral shear, and that led it to rotate, and we can actually see it, that it's spun a little bit, and we can see caught up in the garnet itself evidence that it's spun. Non-rigid body deformation is going to be true strain, so we can have dilatation, which is we're changing our size, so we're going to have a change in volume, so we can have things either being crushed or exploded. So here we have another garnet. This time it's increased in volume. We can also change their shape. So here's an example of, these would have originally, these are rust spots. They would have originally been round, and they are obviously no longer round. So since these are no longer round, we know that we have had some sort of compression to have squished them out, or tension in this way to pull them out. So we know that we've experienced something to change their shape. Some of these things that we know what they originally would have looked like are very useful for deformation, because if we know its initial size and shape, we can determine what has happened to it by what it now looks like. So here's an example of a stretched belemnite, which is a fossil that now has calcite infilling the gaps. So these white areas are areas where calcite has infilled the gaps, so we know this has been stretched out, and so we can determine how much it's been stretched by how much calcite we have in there. Maybe an easier one to understand are these. These are worm burrows, which would have originally been round, so there's a coin here that is round. These are obviously no longer round, so that means that we've had either compression or tension that has led to these things being elongated in one direction. We can tell the direction of that stress. We can also tell the amount of that stress because we know it originally was round, so we can determine how much stress had to have occurred in the rock to change their shapes, which is a really powerful tool. The stress is going to be generated by a thing called loads. So the forces generating the stress on rocks are often referred to as load. There are different types of load. One of them is gravitational. So this is where we're burying rocks, or we have like rock slides. So for example, here we have supports in a mine, and we can see that they are buckling due to the overlying rock. In this example of a exploding magma chamber, we have, sorry about that. Sorry about the dogs barking. So in this example of an eruptive magma chamber, when we empty out this magma chamber, we now have a void. So the gravitational load of the rocks above will cause collapse into that void. We can have tectonic loads. So this would be an example of, this is a model showing us India crashing into the Eurasian plate, and we can see it's just called escape tectonics, but we're basically forcing the plate out. That would be an example of a tectonic load. We can have thermal loads. That's things like cooling. So remember our columnar jointing. That is a shape that is formed in response to cooling. We can also have impact loads. So that is the example of where we have a impactor, obviously, hitting the earth. These are going to be instantaneous. These things are like meteorites. So a load is just what is applying the stress, and there are different ways we get stress. Much of what is being looked at in this chapter is looking at these tectonic loads, a little bit of gravitational too, but primarily these tectonic loads. So deformation occurs when stress overcomes the strength. So all materials have some sort of a strength. Sometimes it's not much. Sometimes it's a lot. So there are different responses to stress overcoming the strength. So we can have brittle response. That is where things break. So here we have fence posts that are broken. We can also have a ductile response, which is bending, and that's this one. So we can either have things actually snap or they can bend. An example of this is when we look at, say, a popsicle stick and we push on either end of it. It will bend for a little bit in the middle until we keep pushing and eventually it breaks. So we go from ductile to brittle in that case. Another example is silly putty. When you pull silly putty apart very fast, it will snap. It will behave brittly. If you pull it apart slowly, it behaves ductily, which leads nicely into my next point. Whether or not materials will behave brittly or ductily depends on many things. One of them is the material itself. Some things just are always going to bend, some things are always going to break. Sometimes it depends on other factors. Some of those other factors are things like time. So if we do stuff fast, it's more likely to break. It's more likely to be brittle. If we do things slowly, we're more likely to be ductile. Rate, kind of the same thing. Rate is actually more of the speed. Time is like how long we're working on it. So you can work on things over a long period of time and then end up having that ductile response over a long period of time. Rate, again, is how fast we're doing it. So the faster we do things, this is the silly putty. We pull it apart very fast, it's going to be brittle. We pull it apart slowly, it'll be ductile. And then magnitude. This is the popsicle stick. If we just push a little bit, we're bending. Push too much and we're going to break it. So there are different responses. So the response can also depend on temperature. So at deeper depths, rocks tend to behave more ductily because of the temperature. So they're more likely to flow as versus break. At shallow depths, things have a more brittle response. So in compression at shallow depths, we tend to have reverse faulting. So we're going to push our hanging wall above the footwall. At deeper depths, we tend to have what we call folding, so we're going to squish up the rocks. Intentional stress, we tend to have normal faulting where the hanging wall moves down relative to the footwall. In the ductile regime, it's going to be stretching, elongation. And then for shear stresses, we are going to have strike slip faulting in the brittle regime, and we'll just have plain shearing in the compressional regime. The difference will be there's not a distinct break in the ductile regime. I think I said that wrong. I think I might have said compressional in there somewhere. So let me re-say the shear. So shear stress in the shallow brittle regime it will be a distinct break where we have two blocks sliding past each other. In the deeper ductile regime, we won't have that distinct break, but we will still see that same pattern of two blocks sliding in opposite directions. That's better. So, few definitions. Brittle means it undergoes fracture, it breaks. Ductile means it has the ability to flow, it's not going to actually break. Elastic is response that is recoverable. So that means we're going to have some sort of a change, a deformation due to our stress, but it can go back to its original shape. So an analog for that would be a spring. If you stretch out a spring, it will eventually go back to its original shape. Plastic is when we have permanent deformation. The analog for that is a sliding block. So if we have a block with a string on it and we tug on that string, the block will move. It can't go back to its original shape, or its original position rather. Viscous is where it will flow under any sort of stress. The analog for that is called a dash pot. You can also think about it as a hydraulic cylinder. So basically you have a piston with oil in it, and so if you have any sort of stress, it will move and it won't go back. Brittle materials can behave elastically and recover by bending. If they break, it's considered plastic deformation. So that is our popsicle stick, that when we bend it and let go, that is plastic deformation. It's recovered. But if we bend it to the point where it breaks, then we have I'm sorry, I said that wrong. If we bend it and let it go, that's elastic deformation. It's recovered. If we bend it until it breaks, that's then plastic deformation. If ductile materials deform and they return to their original form, that's in the elastic. Ductile materials, however, tend to behave more viscously, and so that means they're more in the plastic, and they can't be recovered. So the best example I have for that is if you have like a slinky that's brand new and you pull it apart, it will go right back. So that would be in the elastic domain. If you have a slinky that your 5-year-old cousins have been fighting over, it's never going to go back to its original shape. That would be the plastic. And viscous behavior is always non-recoverable. Once it flows viscously, it's not going to be able to go back to its original shape. So if it's in the viscous domain, it is totally non-recoverable. So let's see what some of this stuff actually looks like. Ductile responses tend to be folding. So how can rocks behave like putty? They can do this if we have very low stress, or I'm sorry, very slow stress. So if we do things over a very long period of time at a very slow rate. If we heat things up, so the hotter it is, the easier it is to just flow. If we have metamorphism, we tend to have both of these things happening. We can have what's called flexural slip, and this is where we actually have basically rigid deformation on the small scale that leads to a large scale bending. So we have layers sliding past each other. And there's also more that I'll be talking about. We can have folds within folds. So basically a fold is where we have this, shape of the rock is folded. It's no longer flat. It's, squished up. On these bigger folds, we can have smaller things superimposed on them. So we can have little folds. That's what we're seeing here. These are little folds on the limbs of bigger folds. We can have small actual offsets, so those would be small faults. We can generate cleavage the same way that we generated cleavage when we had foliation and deformation. We can do that here because this is deformation. We can have joints, which is just breaking apart without offset. Basically, we can have anything on the large scale can also happen on the small scale. So I already somewhat mentioned this. Overturned folds are where we have a limb where the bottom is now above the top. So an upside down fold has been totally inverted. They're kind of rare actually. Overturned folds are not that rare. This is where at least one limb has been overturned. So here we have this one, it would be upside down, it's totally inverted. This one is right side up. This one would be considered overturned. So if we look at this one over here that's considered overturned, if we draw a line, a vertical line down, we will see that this limb, we hit the top before the bottom, but this limb, we hit the bottom before the top. So that's what we mean by overturned. A fully recumbent fold is where it's on its side, basically. So that's overturned to the extreme. I will talk about symmetrical and asymmetrical in a moment, but basically it means, can you fold it in half? And this middle bit is called the fold axis. So if we folded over top of that, would it be the same shape on either side of it? So symmetrical means it is the same shape, asymmetrical means it's not. All right, your book will talk about anticlines and synclines. All books talk about anticlines and synclines. They tend to be wrong. Again, this is from me teaching this class. So the more proper term is called an antiform and a synform. So an antiform means it is convex up. Synform is concave up. So this is an antiform. This is a synform. Anticline means we know something about the ages of the bed. So an anticline are convex towards the youngest beds. I will show you these in a second. It'll be easier to understand. But basically, an anticline means that the youngest is here, the oldest is here. A syncline means that the oldest is here, the youngest is here. You can have a synformal anticline. So a synformal anticline is a synform, meaning it's this shape, but now instead of being the oldest to the youngest like that, it's youngest to oldest. You can have an antiformal syncline. So again, it's that shape, but now instead of being the oldest to youngest, it would be youngest to oldest. All right. So to use the term cline, that means I know something about the ages of the beds. Form is just talking about the shape. This is more than you need to know, but this is me being, I teach this stuff, or I taught this stuff rather. So, all right. Cretaceous is the K, Jurassic is the J, this TR is Triassic. So remember, Triassic is the oldest, Jurassic's the middle, Cretaceous is the youngest. A here is an antiformal anticline, so it's both. All right, so we're in the shape of an anticline, and we have the oldest is we're bending around the old stuff. Okay. If we look at C here, C is going to be a synformal syncline. It's in the syncline shape, and we're bending around the young stuff this time. So if you bend around the old stuff, it's an anticline. If you bend around the young stuff, it's a syncline. Hang on a second, my dog is bugging me. And the second I pause, she gets in her bed. Anyway, okay, so these are what most people think about, but you can also have it differently. So this one down here, number B, that's a syncline, but we're bending around, or I'm sorry, not a syncline, that is a synform. Even I can do it. That's a synform. We're bending in the, it's concave up, but we're bending around the old stuff. So it's a synformal anticline. This one is in an antiform shape, but we're bending around the young stuff. So that's an antiformal syncline. All right, so that can be confusing. Again, this is a little bit more than you need to know, but I like to point this stuff out. So when can you actually use anticline and syncline? If you know the age progression, it's perfectly fine to use those words. If you know the age progression and the facing direction, it's totally fine to use those words. Antiform and synform are used when you can only describe the shape. So if you have, for example, you had your recumbent fold here, and you know the ages of things. If you then had a secondary amount of folding on there, that now we have a secondary fold on top of that primary fold, we would use those antiform and synform. Or if we just didn't know the ages, we can also use antiform and synform. We also have what are called monoclines or isoclines. Actually, monocline is the term for this one. This one is called an isocline, where it's totally, we just have that one recumbent one. A monocline is where it's asymmetrical, meaning we don't have that mirror image, and it's like a step up. These are very common over blind thrust faults. They're actually fairly common. So this is just, instead of having a full area, we're basically just doing this step up. Geometry of folds are challenging to describe. So we have what we call a hinge line. This is the line that's defined by points on the surface of maximum curvature. It does not define our fold attitude. So we're looking at for a single layer, single bed, where are the points of maximum curvature? That is going to define the hinge line. The axial surface is going to pass through successive hinge lines. So the axial surface will be perpendicular to those hinge lines. The axial trace is a line of intersection of that surface with any other surface. So when we're looking at, these boxes are our axial surfaces. So where that axial surface intersects the fold surface, that would be considered an axial trace. So we need to talk about both the hinge line and that axial surface in order to be able to describe the fold correctly. And the hinge line is not going to be the same as the axial trace. So we need to have both of those in order to describe the fold fully. We describe folds in different ways. So we talk about their shape. I've talked about this a little bit. We also talk about the tightness. So this is the angle between the two limbs. So if a fold is open, those limbs are far apart. If it's tight, they're close together. So that's what we're seeing here. A gentle fold is going to be extremely open. And if it's 180, it's not a fold. Isoclines are where you've basically got your two limbs are parallel to each other. We'll make it an isocline. We talk about the size. So the size is going to be the height and width of the fold. So the median trace is halfway down the fold limb, and when we connect those 2 points, we make a median surface. Actually, it's not halfway down the fold limb. It is it's the inflection point. So it's where it's going from convex to concave. So when we're flipping to the next part of the fold. So the fold width will be the distance between those two, or the width of the median trace, the distance between those two inflection points. The fold height will be the distance between the intersection of the axial trace to that median trace. So we're looking for the point of maximum curvature down to the line that intersects the two inflection points. This can get kind of challenging. Symmetry is looking at, if you were to look at your axial trace, do you see a mirror image on either side of it? If you do, that's symmetrical. So here's our axial trace, which again is going to be the fold height is measured along the axial trace, or the axial surface rather. If you're mirror image on either side, you're symmetrical. If you're not, that is asymmetrical. If we go into the 3D, then our folds are now going to be domes and basins. So if you have a antiform in 3D, that will be a dome. If you have a synform in 3D, that's a basin. Oftentimes we will have what we call structural domes and basins. That is based on looking at the age of the units. So here we have the Michigan Basin. In the Michigan Basin, we have the youngest units. Wait a minute, is it the Michigan Basin? It should be the Michigan Basin. Yes, it's the Michigan Basin. Sorry, I'm being silly. The youngest units exposed will be in the middle. Our oldest units will be on the outside. So if we take layers, so these are going to be young, these are going to be old. If we now warp them, so these are young, these are old, and then if we were able to erase, we would see the youngest stuff in the middle, the oldest stuff on the outside. That tells us we have a basin. Whereas a dome, if we do the same thing, young, old, and now we warp them, so we're going to have our old and our young, we will see the youngest stuff will be on the outside and the oldest stuff will be in the middle. So for a dome, we produce that by upwarping, so we end up having the oldest strata in the middle, the youngest strata on the outside, whereas downwarping will produce basins, And so we'll have the youngest strata in the middle and the oldest strata on the outside. So we're looking at our folds in 3D now. Sometimes we don't actually see a difference in elevation going across what we call these structural domes and basins that we have. Basically, we originally had upwarping, but then we had some sort of erosion, so now it's all level. We only see the differences in the ages. That's what we're seeing. I lost my pointer, like here. There isn't really a difference in our height here. They're pretty level, but we can see a difference in the ages. Okay, so now let's move on to brittle. So this is where we're looking at faults and joints. We're breaking our rocks. I already talked about faults a bit when I talked about earthquakes, but let's talk about them again. So if a miner is to stand on the fault face, the hanging wall is where the miners would hang the lamp, so that is the block that's above the fault. The footwall is where the miner would be standing, so that is the block below the fault. How those two faults move relative to each other will determine whether it's a normal or reverse fault. And again, this is only for what we call dip slip, so that's where we're having movement along the inclined plane of the fault. So, if there is no inclined plane, if the fault is basically vertical, we call that a strike slip because the movement is along what we call the strike of the fault. So the strike is the direction the fault is. If we're moving along that direction, if it's slipping along that direction, that's called strike slip. So we can have left lateral, which is called sinistral, or right lateral, which is called dextral. The way you determine that is you have your little person standing on a fault block, and then you look to see how is that other block moving. So if I'm standing there, that block is moving to my right, so that's called a right lateral or dextral. Dip slip is where we have an inclined plane to our fault, and so we're going to have movement that goes along that inclination. So a normal fault is where the hanging wall will move down relative to the footwall. It's moving with gravity. A reverse fault is where you have the hanging wall moving up, opposed, reverse to gravity. If you have a reverse fault that is low angled, so less than 45 degrees, it's called a thrust fault. Many people just use those terms interchangeably, but it's not actually correct to do so. We can also have abnormally low angle normal faults. Typically normal faults are about 60 degrees, but you can in certain situations get low angled ones. So sometimes people talk about a low angle normal fault. And then the final one, oblique, is where we have a component of strike slip with one of these dip slip. So we have a component in both the horizontal and the vertical. So what happens on faults? So if we have stretching, we will get normal faults. So if we start off with our block and we pull in either direction, we're going to end up having a bunch of normal faults because we are going to stretch and thin out our crust. And so we will be accommodating extension. If we have compression, we are going to have our faults be reverse faults. We're going to shorten and thicken up our crust. So we go from our start to our finish, and we can see that with normal faults, we stretch and thin. With reverse, we shorten and thicken. So examples of some of these individual faulting types. Thrust faulting is where we have older on top of younger. What I mean by that is if we have our thrust fault, so we are moving our hanging wall block up, we now have this bed is older than the bed it's now in immediate contact with. The older one is on top. So basically you have a doubling up of your layers. So this is our oldest bed in this sequence, and it's sitting on top of the youngest bed in the sequence. So this is going to accommodate shortening. We can actually have regional thrust faults. You don't need to know these words. I just like to say them. So we can have allochthonous rocks. These are rocks that are out of place. We can have autochthonous rocks, which are rocks in place. So if we have a large scale, low angle reverse fault, we will end up sliding a sheet of rock out of place. If we have an opening through that overlying allochthonous rock that we can see the autochthonous rock, we can see the rock in place, that's called a window. If we have an isolated little bit of a lochthon, that's the out of place rock, that's called a klippe. I just like saying these words. So this happens in regional tectonics that we see this happening. So how do you move a regional thrust? These are very large scale things. So I apologize if you could hear the squeaking. My dog is playing with a toy in the other room. It's honking at me. So this can be aided by things like pore pressure. If you add a lot of fluid into the spaces between grains, those grains are no longer in contact. It's easier to move. It's easier to break. They also don't move as a single mass. So this image is really showing it nicely, like a snowplow. You can also think about it if you've ever shoveled your driveway and pushed your shovel along the snow. It doesn't come up as a single mass. It kind of comes up as these little sheets that fold up on it. And that's exactly what happens with the rocks too. So they're not wedges that we're making individual, what we call ramps and flats. So instead of moving this entire section as one, we're going to make these individual sets that go up. We have these distinct sets of faults that will move up. We can also have what are called tear faults. So tear faults are a type of strike slip fault that forms when we're making large scale deformations. So basically you're having these ones with the teeth are reverse faults. That means a reverse fault where you have little teeth. These ones with the arrows are strike slip faults. So basically instead of trying to scrunch up all this material, it's much easier to scrunch up smaller sections. So we have these individual little strike slip faults that are accommodating the motion or accommodating the deformation, so we can deform a smaller section easier at one time. It's very similar to what happens on our mid-ocean ridge systems, that we have those transform faults so that we're only separating out our ridge one little bit at a time. So we see a lot of strike slip faults that are doing that. They're accommodating larger scale motion by breaking up into smaller blocks. We can have what are called blind thrusts. We're going to hear squeaking in a second. My dog is over looking at her toy chest. So a blind thrust is where we have a thrust fault that's not connected to other faults. It's just by itself. The reason it's called a blind thrust is that oftentimes we don't actually see it at the surface. What we will see at the surface is this buckling up of the material. So we might see one of those monoclines, for example. And we don't know it's there, which is why the term blind is used. So we don't know that it's actually there until it breaks. And when it breaks, suddenly we see why we had that buckling of material. These can be rather dangerous. Normal faults are where we have younger material on top of older. Okay, so what I mean, I always have to stop and think about this. So a normal fault is due to that extension. Again, if we look right here, we see that this is our youngest material and that's our oldest material. So the youngest material is going to be right on top of the oldest material. So we're going to have the younger material sitting on top of the older material. Another way to look at it is like this whole chunk here is younger than the bedrock over here, and they're in contact. So if you have younger on older, that means we have extension. So that's normal faulting. So the normal wall or normal faulting, the hanging wall moves with gravity. It moves down with gravity. So this used to be connected to that, and it's moved down. These are very common at mid-ocean ridges because we have extension at mid-ocean ridges, because remember what's happening is we are spreading the ocean crust. So normal faulting is very common at mid-ocean ridges and continental rifts as well. We can have a special type of structure called Horst and Graben. Horst is a block that is bounded by normal faults that has dropped. Graben is the downward dropped. Horst is a block that has not dropped, that's bounded by normal faults, and the Graben is the part that has dropped down. So this is the Horst, that's the Graben. Graben means ditch. I was taught it meant grave, but when I started talking to a native German speaker, he's like, nope. I looked it up and it's like, yeah, it's ditch. This is where we can get some of those rotational faults that I talked about earlier on in the lecture, the listric faulting. So these can curve at depth, and this is where we can get low angle normal faulting too. And then finally we have strike slip faulting, which in many cases it's to maintain volume. So I already mentioned tear faults that basically allowed us to deform a larger area by breaking that area into smaller sections. We also see this in mid-ocean ridges. We can also have strike slip faulting where we're moving from one set of motion to another set of motion, or one sense of motion to another sense of motion. We often will get them also when we're moving between fault sets. So again, we get these along mid-ocean ridges. We can also get them along, basically we can get these transform faults connecting any type of plate boundary. So you can get them along ridges, you can get them along trenches, you can get them when they're transferring between trench and ridge. We can also get some really interesting things happening with strike slip faults. So if you have a strike slip fault that takes a turn that's not perfectly straight, when it makes that turn, when it bends, it will actually have additional faults in that area that will be either normal or reverse depending on what is happening with the direction the plates are moving, as well as what direction the bend is, and we call these flower structures. They're also called duplexes. So if we have tension within that bend, it's called a reverse flower structure, or a negative flower structure, because we have extension happening. If we have compression happening, it's called a positive flower structure because we have material being pushed up. And so the reason we call them flower structures is that when we look at the cross section, you see this down drop or up drop, and they kind of look like a flower. But you can get, there are 4 different ways you can configure your bends and your motion, and so you get different structures depending on if you have which direction the bend goes. When we have a fault, it leaves a record on the Earth's surface. So the offset in the land surface that coincides with the fault is called a fault scarp. That is when the blocks have just moved. This will eventually be replaced by what we call a fault line scarp after weathering and erosion. And actually we can have the sense of offset be changed due to differential erosion. So if we're looking at an old fault, sometimes what we see at the surface is not indicative of the actual sense of motion because we've weathered away that it looks like it is. We can actually have a normal fault due to extensive erosion will start to look like a strike slip fault. There's some interesting things that can happen, and so that's why we have these 2 different terms. We have a fault scarp and then a fault line scarp, because that fault line scarp is no longer necessarily showing us the accurate sense of motion. The other type of brittle deformation we have is called joints. This is where we don't have offset. We're just having tension. So we're just extending things. There are different ways that we can have joints opening. Joints are actually extremely important for the Earth. For example, they lead to weaknesses in rocks, which then allows things like water to percolate through, which can then lead to weathering, which is why we can then start to have different things developing. So joints are a very important type of deformation on the Earth's surface. They happen everywhere that you have some sort of extensional force happening. It can be a very localized extensional force. It can be large-scale extensional force. And so this is something that is basically leading to a weakness on the Earth's surface, and that will then be an area that will be concentrated on for things like weathering and whatnot. So what happens with mountain building? We have a lot of mountain belts on the planet. They are various ages. This map is showing us the shields, which are the nice stable old crust in yellow. The shields are the oldest part of the crust. The gray is the stable platforms, so shields that are covered by sedimentary rock, which are nice and stable. Then we have young mountain belts, which are in red. These are the ones that have happened due to fairly recent collisions. And then we have the old mountain belts in purple, which are the ones that are due to old collisions. These collisions, most of these major mountain belts are due to continental collisions. So the first step is going to be subduction, the next step will be collision. So again, subduction, if we have ocean-ocean, we could produce island arcs. So these are just volcanoes that are coming off of, up through the ocean crust. If we keep subducting our oceanic crust, eventually we'll consume, if it's only oceanic plate, we consume the entire plate. If that oceanic plate also has continent on it, then that continent comes along for the ride. So when you're subducting oceanic plate beneath continent, you produce mountains instead of just volcanoes, because you're going up through this you're thickening that continental crust. So you make a continental volcanic arc. So the Andes are an example of doing this. So it's a pretty impressive mountain range, but the really impressive mountain ranges come when you finish subducting that oceanic plate, and you may bring along a microcontinent that then gets what's called accreted or stuck onto the continent. You get massive uplift because you basically have multiple layers of lithosphere stuck underneath that continent too. And the extreme of this is going to be true continental collision. So the end result of subduction will always be continental collision at some point. It may be millions of years down the road, but at some point you will have these continents colliding together. That's the Wilson cycle. So this is what we're seeing with the Himalayas. I've talked about this a couple times now. So all of these all of these mountain belts, are due to different collisions. Some of them you can see where the collision has happened. Other ones, the Appalachians used to be connected up to these other older mountain belts, and then they've been split. All right. I think this is the last part and I'm covering as far as lecture material in this bit. It's called isostasy, which is vertical movements of the crust. I honestly can't believe that your textbook covers this, but they covered it, so I'm going to do it. This is a rather advanced topic. I teach, or used to teach, seniors and grad students this topic, and some of them still had problems with it. So hold on. Isostasy. Isostasy is the equilibrium in floating. So we are basically looking to see if there is what we call compensation, if there's something that supports the elevation on the planet, and that's what isostasy ends up being. So gravity measures whether or not we have that equilibrium. Okay. We can reveal global deformation and anomalies in the mantle with satellite imagery of our gravity. So Archimedes' principle is the principle of floating. So the weight of displaced material is going to be equal to the weight of material causing displacement. That's what floating is. So that's what we see here. That's not right. This one's floating. That the weight of this should equal, when it's totally floating, that we don't actually have a mass. It's floating on here. It's not pulling anymore. The weight of this material in here should be equivalent to what has displaced it. That is what floating is. So the decrease in weight is equal to the amount displaced. So basically, if we're somewhere in the middle, so we've got here, we have a weight being decreased, the amount that we've displaced is going to be equal to that displaced weight. And then when we're fully floating, that we don't have a weight, the amount we've displaced is going to be equal to the amount of the thing that's floating. Depending on the density of the fluid you're trying to float in, or the liquid you're trying to float in, if it's more dense, it will float easier. So there's less displacement that will occur. If it's less dense, it either won't float, or it will take longer to float, more displacement. It also depends on the material that you're trying to float. So it's much easier to float a thing of styrofoam than a thing of wood. And that depends on the masses and the density, or rather the densities of the different material. When you have sinking, that is when you have the material is not dense enough to support the liquid is not dense enough to support whatever's trying to float. And so you will have the volume is equal, but the weight's not equal. So you'll displace the same volume, but it won't be the same weight. Isostatic equilibrium is when the blocks are showing no variation in gravity. So we have support for the elevation we see at the surface by something in the mantle. So that support can come in two different ways. It can either be due to density contrasts. So basically we have more dense material supporting, or I'm sorry, less dense material supporting the elevation, so it's letting it float higher. Or we can have extra material that's supporting it. So an iceberg, we see just a little bit of the iceberg at the surface because there's a lot more iceberg below the water level. So the more iceberg below the water level, the more iceberg we will see above the water level. So that's one way of compensating. The other way is if we have different densities. So that's the idea of you can float yourself a heck of a lot easier on an inflated pool float than sitting in the water yourself. You have different densities at that point. So one of the things that we're always looking at is, has there been something to account for a mountain? Is there something supporting that mountain? If there's nothing supporting that mountain will respond basically. So if we push things down, they want to come back up, or if we lift things up, they will go back down. So we can actually change our elevations due to the fact that we are changing heights. It seems really strange, but it can happen. So an example would be if we have an ice sheet. So an ice sheet is a nice heavy mass that is sitting on top of the crust. That will push the crust down, which will push the asthenosphere away. If that ice sheet melts, suddenly it's not in balance anymore because we've pushed away the asthenosphere. So the asthenosphere is going to want to flow back in, which will lift up the crust. And so we will have what's called isostatic rebound, that the crust will lift up. We are currently experiencing that in the Michigan Basin, actually. The extent of the last glaciation, we're still rebounding from that. We're still lifting up. And so we will have a difference in that height. We can figure out what that difference is. You don't have to do this. You will not have to do this, but we can figure out what that difference would have to be between, ice was here, we've removed the ice. So basically the ice in this case is going to move up by almost, or a little bit more than half a kilometer, which is pretty impressive. I'm sorry. So in this case, the ice is, the land surface will move up, but we will also, the land surface will move up by that, almost half a kilometer, but we can see that the ice was higher than the original sediments, but we're not going to rise up to the level of that ice. Here's an example of a filled basin. I'm stealing these from a textbook, and I don't like the way that they do it. So the filled basin is basically showing us that filled basin is deeper than the original lake. So this first one is showing us a lake, and then we basically filled in that lake. So that filled in lake is deeper than the lake itself because the sediments will compact under its own weight. And then, we are going to basically push down the material. So if we, if we have extra material we will push down, which gives us a depression, which gives us more material we can push down, which will give us more of a depression. So once you start digging a hole, it will keep getting deeper. Conversely, if you start removing material, the underlying material will want to rise up as well. So erosion will actually make mountains build, because basically if you start removing material, then you're in an imbalance, so it's going to want to bob up. So then you can remove more material, which will make it bob back up. So mountains can actually grow as a result of erosion. So we can look at these as two end members. We call these Airy and Pratt. So airy is the idea that we have what are called roots. So there is extra material beneath the crust. This is why the continental crust is thicker. That is going to be supporting that elevation. Pratt is the idea that we have density variations. I'm sorry, this is the one that really explains the continental crust. So Pratt is the idea of we have different densities of material. So oceanic crust is denser than continental crust. So that's why the oceanic crust will sit a little bit lower than the continental crust, and we have that elevation of the continental crust. The reason why we have big mountains like the Himalayas, they have a root. They have extra material below them that's supporting them. So we have to have these two things working together, and we can look to see what the amount of compensation is so we can figure out what's happening. So what will happen is that we will simplify this. The Earth isn't made up of blocks. We oversimplify it. The lithosphere has some strength. So there are certain amounts of load that we can compensate with the lithosphere. It can just sit there and not bend. But eventually, if we add a big enough load, the lithosphere will bend and will push away the asthenosphere. So this is where we're going to have regional. So this is where we're going to have regional compensation. So, for example, if we have a load of ice sitting on the crust, it will push down the lithosphere, which will push away that asthenosphere, and so that will be a short-term compensation. If that load is then removed, that asthenosphere will want to move back in, and that will push the lithosphere back up. So isostasy is the amount of support that is underneath areas. And so we look at what we call the anomaly. So we're going to look to see whether or not there is compensation. So areas that have compensation due to those roots will show no what is called free air anomaly, but they show a negative Bouguer anomaly. This is in our gravity. Areas that have no compensation will not show any sort of a Bouguer anomaly, but they show a positive free air anomaly. So basically, we can look at these different ways of measuring gravity. Well, we measure the gravity the same way, we just do different calculations to it, and we can see what the amount of compensation is. So this tells us, is there a root? If there's a root, that means that we're not going to have significant up or down. If there is no root, that means if we have this elevated area, something has to happen. So that's what we're seeing here, is that we're basically able to predict how much vertical movement there should be based on the relationship between these two calculations. So Earth is extremely complex. The area and Pratt isostases are end members. Compensation can be either incomplete or a hybrid. So we may have variations in density as well as having additional material. So we're going to calculate the gravity of a fully compensated area and then subtract our free air anomaly. And this will test the amount of compensation for whichever model we're assuming. We have to assume one or the other. We do see this in the world, along the globe. So the idea of isostasy was first proposed after we found that mountains only have about a third of the gravity variation expected because of their mass. So we realized that there had to be less dense material at depth that was supporting it. The other thing we see is that the lithosphere can sag under weights. So for example, that's what we're seeing here, the Hawaiian Islands. So if we look at the gravity anomaly going across Hawaii, we see these negative anomalies on the edge of Hawaii. If we look at the bathymetry or the ocean floor, we actually see that it dips as well where we see these negative anomalies. So the lithosphere is literally sagging under the weight of Hawaii. And I've already mentioned this, isostatic rebound is that where we have those large loads, they make the asthenosphere flow away as the lithosphere is pushing down. Once that load is removed, or if that load is removed, then the lithosphere comes back up as the asthenosphere is flowing back in, and this is what we call rebound. So we see this typically with the removal of glaciers. Then when we have large-scale ice sheets and those are suddenly removed, then the lithosphere can bounce back up. So this is an example of Fennoscandia that we're seeing uplift from the removal of ice sheets. And we can actually use this to determine how much ice sheet was there. So we can look at these different anomalies to determine how much vertical movement have we had, how much more can we anticipate to have, and we can calculate how much ice was there in the past. So this is being used a lot in Antarctica to determine the extent and the thickness of the various ice sheets in the past. So we're looking at how Antarctica is adjusting. When we're looking at it specifically from ice, we call it glacial isostatic adjustment, or GIA, and we can determine based on the uplift or drop down how much ice has been there in the past and has been removed. So it's a powerful tool for looking at past glaciations. Okay, so that is, you know what? I'm going to go ahead and show the pre-lab video for this week now, and then I will go into test taking 101. So let me pull up our pre-lab video. So this pre-lab video is for...
Hi everybody, this is Callan.
This is for volcanism and volcanic hazards. This is for 2023, I may change up the order I do things. If this is no longer the pre-lab video for your week, please do watch the appropriate pre-lab video. This one's rather short. It's only 5 minutes long.
Yep. Welcome back for another pre-lab video. This week in lab, we're going to be taking a look at volcanoes and volcanic hazards. We're going to be examining what makes some volcanoes explosive and other ones effusive when they erupt. We're going to be examining the differences between shield volcanoes, cinder cone volcanoes, and composite volcanoes. And lastly, we'll be taking a look at volcanic hazards. Let's begin with this chart from your lab manual that shows the variations in composition and how that affects the volcanoes that we see. Lavas can be relatively felsic or they can be relatively mafic. Felsic means it has the most silica in it, around 70%. Mafic means the least amount of silica, and that bottoms out around 50%. In between is intermediate. The gas content correlates with the silica content, so mafic lavas have the least amount of gas, generally only up to 2% by weight, and felsic magmas have the most gas, up to 8% by weight. The eruptive temperature tends to be the highest for the mafic lavas. It tends to be the lowest for the felsic lavas, and this has a big influence on viscosity. So viscosity is resistance to flow. You might have heard that blood is thicker than water, blood is more viscous than water, honey is even more viscous than blood, and motor oil is even more viscous than honey. In the same way, these felsic lavas are more viscous or resistant to flow than their basaltic counterparts. And as a result, the basaltic eruptions tend to be really runny and fluid, and the felsic eruptions tend to be very sticky. And this ends up basically making different shaped volcanoes. If the volcanoes are very runny, then they ooze out over the landscape and they make these big, broad, shield-like platforms, shield volcanoes, as well as basaltic plateaus. And if it's a felsic lava, then you end up getting these explosive eruptions that have a lot of pyroclastic material, and they tend to form these pyroclastic flow deposits. In between are these andesitic composition volcanoes, which end up giving us composite cones, such as the Cascade Range in the Pacific Northwest. So one of the ways that you'll explore this in lab this week is to take a look at a series of images. These images will be of volcanoes, of volcanic landforms, and of volcanic products, and you'll be asked to evaluate them on the basis of their evident viscosity, their resistance to flow. This will help you determine whether these are mafic, felsic, or intermediate volcano. Another way you can do this is by estimating the slope of the side of a volcano. Here, Mauna Loa has a relatively shallow slope, only a few degrees away from a horizontal. That indicates it's a shield volcano. It's going to be made out of runny, effusive lava that's mafic in composition. Cinder cones, on the other hand, might tell a different story, and they would have a different slope, a different angle from horizontal down to the ground. They also have interesting morphology that can only be viewed from the air. Finally, we'll take a look at composite volcanoes, which have both lava flows and pyroclastics making up their bulk. Again, there'll be a different angle relative to horizontal. Finally, we turn our attention to volcanic hazards. Volcanoes are a source of a great many different sorts of hazards, including pyroclastic flows, some of the most deadly, Lahars, which are volcanic mud flows, we'll take a look at in detail. Collapse of the flank of the volcano or a lava dome, projectiles such as bombs, ashfall, and even good old lava flows. We're going to take a look at Mount Rainier in the Cascade Range of volcanoes, which has generated some serious mud flows in the past. And we're going to give you a map, and you're going to be asked to make some calculations about how quickly these mud flows go down these various drainages towards different towns in the Puget Lowlands area. Finally, we turn our attention to ash. Here's a pyroclastic flow, but we're going to take a look at ash fallout from the eruption of Mount St. Helens in 1980. And then that eruption was also very violent right in the area of Mount St. Helens with a flank collapse of the volcano. So you're going to take a look at the damage area there and be asked to evaluate a few things about how that eruption went down. So that's a preview of what we're doing in lab this week. Good luck, and thanks a lot for watching this pre-lab video.
All right, hopefully you could not hear my dog. She was violently licking herself throughout most of that video. So now I'm going to talk a little bit about test taking 101. So this is obviously specifically for this class, but this should also relate to many of your other classes. So what are you going to study? If you're given a study guide, make sure you look at it. For example, in this class, there is a tab in the navigation pane that says study guides. Each exam's study guide is released after the previous exam, so you now have access to 3 of those study guides. If the instructor emphasized anything in lecture, review that. Did the instructor go over something multiple times? If they did, that's probably important. If it's been discussed in multiple class periods, multiple labs, that's probably important. If you've seen the same thing in multiple lectures, quizzes, labs, that's important. So make sure anything that has been gone over multiple times that you understand it. Do you have your old labs, quizzes, exercises? Those are good things to go over, especially anything that's been written or given to you by the instructor themselves. That is stuff they think is important. So if they're writing the exam, that's probably the stuff that's more likely to show up on the exam. If there's anything you find confusing, ask questions. That's what office hours are for. Office hours are so you can ask questions. They're not just so your instructor can twiddle their thumbs or grade papers. They are for you to ask questions, so do ask questions. Office hours are to help you. Office hours are definitely the best time to find me. There are times when I will be leaving campus to go let my dogs now out. I made this slide back before I had 2 dogs. So the office hours are a time when I am dedicated to be there. Email is also good. How to take a test. Take your time. Seriously, take your time. You have 2 hours and 20 minutes to take these tests. Read all the questions. Think about them. Read everything. So, both of the exams in 2023 had a bonus point if you read the instructions. Not everyone gets those bonus points. Surprisingly, some people got those bonus points, but did not get this one. Both exams have non-bonus points, meaning it's part of the exam for putting your exam number on all the pages. There were people that did the bonus thing, either drawing a smiley face or a star or whatever happened to be the instruction on that one, but they didn't put their test number on the pages. So read everything. Some people miss both of them. Make sure you're answering the question that is asked. For example, in the first exam, there's a question that was asking you to label planets as either Jovian or terrestrial. I have had people label the planets by their names. That is not what I asked you to do. Make sure you're actually answering the question. If you're not penalized for a wrong answer, which normally that only happens in true standardized tests, then put something down for every question. While it makes my life easier to be able to say 0 on a question, it frustrates me. The only times I have put a 0 down in 2023 are when there is nothing written down on the page. People that wrote down, I don't know, or I should have known this, but I forgot, still got 0.1. I will also give points for people that make me chuckle. I very rarely will give you a 0 on a short answer question. I can't really help you on the matching true false, whatever. Final thing, make sure you go back over your answers. Make sure they make sense. Make sure they're legible. If I am asking you to write down letters, make sure I can read the letters. I am often staring at these letters going, is that a T or an F? That is very frustrating. Make sure I can read it. Look for answers elsewhere on the test. Now this is from, I made this up before I started letting people do, that we started splitting the test into two. So now that we split the test into two, this isn't quite as applicable, but you still might be able to do this. So if you forgot Cretaceous, maybe it's in one of the multiple choice questions. Again, now that we're splitting this up, you can't really do this. Here's an example of how you could use from this particular exam. So this was from the second exam, the fill in the blank with the Mohs hardness scale. There were several of them matching that were based on Mohs hardness scale. Now I did have people asking me, can I go back and change something? The answer to that is no. Now that I am letting you work with a partner on the multiple choice and the matching, that means you don't have those questions that you can go back and check things on, unfortunately. But you still can sometimes find, things in other questions. Like I saw people basically trying to use streak for answers for a bunch of other questions because I'd used that in one of my questions on the short answers. So sometimes you can find spellings or it might give you an idea. So look over the exam to see if there's other things. And there are definitely still ways that you can work things out on just the multiple choice and the matching. So basically, I told you talc was number one on the Mohs hardness scale if you had both pieces of the exam at the same time. I told you that diamond, or you should, by process of elimination, you should have been able to figure out that, hardest mineral, diamond's one of the options. Diamond should probably go there because you hopefully could remember gypsum was not hard. Look over your test again. I haven't done the statistics. I am now writing down the amount of time people are taking. Some people are only taking 10 to 20 minutes to do their short answers. In the first time I taught this class, people were turning in the entire test in, half an hour or so. If you have 30 matching and 30 multiple choice, that's less than a minute, way less than a minute per question. Did you even have a chance to read and think about your answers? So basically, take your time. Think about it. Sit back. Think about it. Don't rush yourself. And that is all for this week. So that is crustal mountain building and how to take a test.